So once again, a very kind welcome to everyone. Thank you for your attendance and for your interest in this very challenging yet interesting topic on managing water challenges in cities. We have the pleasure here to have a very interesting panel of speakers, not only from city pilots, NAIADES city pilots, which are the city of Carouge in Switzerland, Alicante in Spain, and Braila in Romania, but also a number of partners who are working with us in NAIADES on the same topics, trying to find synergies and solutions to support water management in the cities. So we will not spend a lot of time on the introduction because we have quite an interesting session and quite a challenging session at the same time, but just a few notes. This session will be entirely recorded and published on the NAIADES channels, so we will be able to also find the same video on YouTube later on. Please feel free to post whatever questions you have in the chat. We will try to address them during the meeting, and also to share your experiences and tweet about this on the NAIADES project Twitter account using the hashtag NAIADES webinars. I'm very happy to interact with you through social media as well. So my name is Eunah Kim. I'm project manager at Mandate International in Switzerland, in Geneva. I am a specialist in environmental science, also with a background in international relations and business management, with a clear focus on sustainable development goals. And I'm happy to be a part of the NAIADES project, leading not only the sustainable development side, but also the communications and international cooperation for the project. And in this framework, we are organizing a series of webinars each month regarding topics that are close to the NAIADES project. And we are in this framework organizing this session, which we're hoping to have very interactive results with the audience, which is why we're very happy to have you here. So this is the agenda for today. It's quite challenging. As you can see, we have 3 key sessions, each for each of the pilots, but also a number of feedback sessions where we will ask you to participate through a interactive manner. You will get the details in a second, but we are very happy to have you all participating in them. Please note that the 4 feedback sessions that we will have at the beginning are for all the audience, so everyone is welcome to participate. And for the final one, we just would like to ask the NAIADES partners not to reply to this, to just allow for the external speakers who are not part of the NAIADES team to provide their feedback. This is just a little disclaimer. And now we can move on with the rest of the session. So how will this work? Basically, as you can see on the screen, we have a link to a site that I kindly ask you to join. You can either type this on your phone, on your computer, whatever works better for you, or you can also scan the following QR code, which will directly take you to the page that I'm asking. If you could please do so, we will be able to start with a really small feedback session from you, just as an introduction, a number of small questions. And we would like to have your feedback on this. I will switch, of course, to the present mode. There we go. And I kindly ask you to reply to the following question. In general, how much do you believe information and communication technology and AI services improve water management in cities? So as a reminder, in order to answer to the question, you need to log to the address ahaslides.com/SW2022. I will also share with you the link to this in the chat box. Thank you, Eunah. It's already in the chat box in case you want to access the questions. You can see there's some bit of interaction going on. So thank you very much for your clear votes. There is quite a significant choice for the extremely improve it, which we're very happy about because this is at the core of our activities, and we're hoping that we're going to get further replies from you on the next questions. So another question we would like to ask you as an introduction is the following one. What are, according to you, the main challenges of water management in cities? And here you can choose from a number of different options. The pie is moving into a beautiful rainbow. Water stress could be anything going from water scarcity to flooding, lack of availability of water. All right, so thank you for your replies. As we can see, there is quite a significant disparity between the results, with a winner for increasing vulnerability to severe weather events, followed by resource constraints. So now that we're on the topic, we will not keep on doing any more feedback sessions, but we just wanted to test as well with you how it works. So very happy that you are on board with us. And we will now move on back to the slides, back to the topic. And I will give the floor right now to our coordinators, Thanasis from CERTH, and also Elpiniki later on, she will join us. Thanasis, I would like for you to just give us a little introduction about your background, and we welcome your presentation.
Hello, everybody. Thank you for the introduction. My name is Thanasis Anagnostis. I work at the Center for Research and Technology in Greece at the Institute of Agri-Technology and Bioeconomy. I worked there for the past 8 years, and my specialty is machine learning applications and data-driven technologies. That's all from my side. We can move on with the presentation. So I will be giving you an introduction to NAIADES. Can you see my full screen?
Yes.
Okay, good.
Just need to put in full mode. Yes.
Sorry, give me a minute. Okay, so NAIADES is a project from the European Union. Its main goal is to create a holistic water ecosystem for the digitization of urban water sector. So in order to create an end-to-end uniform approach, NAIADES was developed to redefine water management by taking into consideration issues regarding cost, safety, complexity, vulnerability, societal acceptance, user behavior, and ethics. The coordinator is as the Center of Research and Technology Hellas, and the duration of the project is 3 years, planned to be completed a few months from now by May of 2022. NAIADES supports digitization of the water sector by providing a holistic solution for the control and management of water ecosystems through a sustainable and eco-friendly water management. The project consists of 18 consortium partners, more specifically 8 research institutes, 6 SMEs, 1 university, 1 municipality, 2 water utilities. They all participate in the project. In the map, you can see the location of our partners, where the pilots of the project are highlighted in yellow. So the NAIADES project targets in the following 5 main objectives. The first one is to harmonize and integrate different water EU vocabularies and data by developing translational data capture tools. To accomplish this objective, NAIADES created the core architecture of the platform compliant with the FIWARE framework, an open source platform which accelerates the development of smart solutions. This enables end users to create data models aligned with requirements of the European Telecommunications Standards Institute. The second objective of NAIADES is to support innovative methods and technologies for data analytics, open APIs, and interoperability. By adopting FIWARE standards and data models, the NAIADES solutions are compatible with any other platform which is based on the FIWARE framework. Next objective is to provide end users with various services based on artificial intelligence. Some of the developed services give useful insights about better decision-making on water consumption and quality, water-related anomaly detection, and weather prediction. Part of the NAIADES solutions are the water consumption awareness apps and dashboards which can enhance awareness for water management companies, public employees, as well as water consumers. And finally, however, a key part of NAIADES is the developed security toolkit, which ensures data integrity throughout all processes of smart water management. The proposed ecosystem and business framework development in NAIADES is validated through demonstration in 3 areas: Alicante, Braila, and Carouge, located in 3 different countries. Pilot use cases aiming to present the high adaptability and flexibility of the proposed solutions. The operational properties of the technologies and overall solution will be validated and evaluated against performance, effectiveness, cost, acceptability, and usability indicators. The problems associated with the pilot's use cases are water demand prediction, saline intrusion detection, water consumption awareness and behavioral change support, leakage reduction, treatments prediction, plants watering, and fountains management. NAIADES will validate the proposed technology framework through pan-European demonstrations in heterogeneous water management areas, cycles, and value chains, and use case aiming to present the high adaptability and flexibility of the proposed solution. For that reason, several pilots will be deployed in the last part of the project. In fact, the proposed ecosystem and business framework developed in NAIADES will be validated through demonstrations in 3 areas: Alicante, Braila, and Carouge. The operational properties of the technologies and overall solution will be validated and evaluated. Sorry, I'm repeating myself. Okay. In general, the overview of the NAIADES ecosystem platform is depicted in this figure, highlighting the main components of each level, such as the data collector and aggregator, which adapts end users' data to the NAIADES specifications, the data model validation, which rejects the data if the data model format is not correct, or if the signature validation fails, the data manager which circulated all platforms data, the AI services which consume and generate new data, the decision support system which presents outcomes on a dedicated UI, the marketplace that showcases the NAIADES solutions to potential clients, external end users, and service providers. Main components of the platform are pilots, DCAs, and tensors. The orange and red components belong to the NAIADES ecosystems and are provided by the NAIADES partners to adapt end users' data to the NAIADES specifications. All the data management in the platform goes through the data manager. The DMV rejects the data in the data model format if it's not correct and the signature fails. The services, the yellow components, are consuming data from the pilots or generated by other NAIADES components. From the data manager generating new data and sending it to the data manager. The services on the top of the architecture, water consumption, water observatory, and awareness and behavioral change support, are services that present their outcomes on a dedicated user interface. The users access this dedicated UI from the NAIADES HMI. The marketplace has an independent UI and showcases the NAIADES solution to potential clients. The main innovations of the developed platform are its interoperability, modularity, and scalability, as well as its security. So, concerning interoperability, the first innovative feature of NAIADES is the complete interoperability of the system. It basically fosters the communication between end users, service providers in various sectors. Also based in the designated tools, data can be seamlessly collected and integrated into the platform in order to feed the NAIADES smart water management services. Some of these tools are data collector aggregator, common data models, and data models validation. Concerning interoperability, 3 indicated tools have been defined. Concerning the second innovation, a set of state-of-the-art solutions relevant to the NAIADES end users are provided. Some of the innovations provided to the end users are the dynamical treatment suggestion for drinking water treatment plants, the data fusion middleware for extended data pre-processing, the consumption awareness dashboard, and the water quality predictions for preventive measurement. The third innovation is relevant to security. NAIADES harness the advantages of the blockchain technology through the keyless signature infrastructure. The developed tools based on the blockchain technology enable EU-based water utilities to connect with the NAIADES platform, validation of the authenticity of the data, and early warning protection for critical log and event feeds. Here we summarize the main functionalities of the NAIADES ecosystem. The first one regards solutions which are designed to solve current issues of 3 different end users and can be adapted to other water utilities. Secondly, the platform is compatible with a FIWARE-based data model, since NAIADES data models developed according to the FIWARE standards. Thirdly, thanks to the NAIADES ecosystem, the platform provides secure, flexible, and interoperable solutions. And finally, one of the advantages of the platform's components is the plug-and-play functionality, as they can be adjusted to work with new installed devices. However, NAIADES also provides effective management of water infrastructure and staff through monitoring of critical water consumption and the measurements from different sensors. Thanks to the NAIADES services, end users get useful insights by weather prediction, water demand, and quality prediction. Additionally, the decision support system of NAIADES is an important part of the platform, since it provides early detection in systems flows. It fosters the communication between stakeholders with different roles and supports maintenance procedures. Also, NAIADES' primary goal is the user awareness and behavioral change support. Therefore, NAIADES' innovative solutions effectively inform water management companies and public officials about water consumption. Some indicative screenshots of the user interfaces for each one of the 3 pilots are presented. In the first screenshot, the pilot is informed about the current status of the water quality of the city's fountains. Next, the water utility in Alicante. Sorry, this is about Carouge. Sorry, there is a mixed one. Next, it provided a dashboard where analysis of the weekly water consumption can be efficiently monitored. Sorry, and for the third pilot, several graphs about historical data are provided along with predictions about leakages and pressure. Okay. Thank you all for your attention. And if there are any questions, I think, Anna, we move all the questions to the end, correct?
Yes, that's correct.
Thank you very much.
Thank you very much for your presentation. Now we can move on to our first pilot, which is Carouge. Maurizio, I will give you the floor, and I will also let you introduce yourself.
Yes. Thank you very much. Good afternoon, everyone. So thank you very much. My name is Mauricio Rossi. I'm a project manager at the city of Carouge, where I'm in charge of coordinating the NAIADES pilots. I have a background in the art and humanities and in the IT. I've been working in the IT for the last 15 years as a researcher, as a computer scientist, and as a manager at several research institutions. Our presentation today with our colleague Eunah will focus on the use cases in Carouge. I will first give a little bit of background information regarding the Carouge situation, the reason why we participate in this project, and then I will give you a little bit more details regarding the use cases itself, and then I will give the floor to Eunah for a more in-depth sight into interoperability, how it is implemented in NAIADES, and the potentials it can unfold. But first of all, some key facts on Carouge. I will try to go as quickly as possible. We have a lot of stuff to present. Please, if there are any questions, I would be very happy. We will be very happy to answer at the end of the presentation. So Carouge is located in the Geneva canton. It's which is a global financial center and also home to several international organizations. Geneva itself has a lot of industry and most of all a lot of services industries. It's a relatively small city. However, it provides more or less 20,000 jobs, workplaces, and it's also a city that has been growing very fast. The population has almost doubled in the last 30 years, and at the moment, population is about 23,000 inhabitants. One fact important to mention is that while the population is growing, the budget often is not growing as fast, and so there are pressure for the city to provide the required amount of services with a limited budget. The city of Carouge is also very active, very committed with sustainable development. There are efforts to wisely use natural resources and undertake undertake sustainable actions for the environment. This activity by the city of Carouge has been awarded with several labels and awards. And among other things, the city of Carouge is the first city in Switzerland who has committed to become a zero waste city. So there is a strong will by the city council to improve its own water usage and also to promote responsible water consumption beneath the citizens. There is also strong demand actually by the citizens to move towards a more sustainable management of the natural resources in general. The participation to the NAIADES project as one of the pilot cities is consistent with this effort, and therefore the city is looking for technological solutions that can help to achieve this goal. Of course, the city is not looking only at technological solutions, but the technological solution could be a part of the answer to these challenges. The city of Carouge is also a smart city pioneer, has been participating in several research projects in the past, and it has an existing smart city infrastructure, in particular a LoRaWAN network, which is actually managed by the SCG, which is a public utility company in the region of Geneva. So, geographically, Carouge is situated at the heart of Europe, at least geographically, and as you can see, it's on the shore of the Lake Geneva, which is one of the biggest water reservoirs, one of the biggest water reserve in Europe, and it's also located nearby the Alps, which play an important role in providing, in collecting water from precipitation, from the rain, basically. So when one looks at this picture, could believe that water is not actually a problem yet in this region, because there is a lot of water available. However, this is not always the case, as we will see just in a while. The water in Carouge is provided by the public utility, the Service Industriel de Genève. So this is a public utility company, but the city is not providing itself the water. So the city is actually a customer of the public utility company. Mostly of the water consumed in the region comes from the lake, about 90%, and 10% is coming from deep wells underground. As I just said, water scarcity is not a major concern at the moment, but it's an increasing problem. It's an increasing threat. On one hand, due to climate change, we are observing increased episodes of droughts in the region. And of course, in the midterm, the shrinking glaciers in the Alps will be a real issue because of the role they play at the moment with regulating the water flux and so on. We have another problem which is already there, which is already a real problem, and which is the contamination of the soil by several sources of contamination. A few years ago, vast pollution by perchlorates has been discovered on the underground of the area, and which obliged the authorities to close down a significant part of the wells, which had as a consequences that we went from 20% of water from underground down to 10%. So now let's focus a little bit on the two use cases implemented at Carouge. These two use cases have been selected by the city relevant departments, in particular the service which is in charge of the water related issues. we identified two potential use cases. The first one is the watering of flower beds, and the second one is the water management in public fountains. The city has two general goals with this project. The first one, of course, is to decrease water usage by further optimizing it. And the second goal is to reduce the workload by improving the efficiency of the processes. So the first use case is the watering use case. As I mentioned, Carouge is a blooming city. It's a truly a blooming city. It's a peculiar characteristic of the city of Carouge. Its flowers, they are really well known and appreciated, pretty much appreciated by the citizens. Carouge is also awarded on a regular basis for its flowers, for this effort. There are more or less 180 flower beds around the city, and also some green areas. There is an effort going on apart from watering. Apart from water, there is an effort on sustainable towards sustainability, and therefore there is a focus on choosing local species of flowers, and there is a transition towards pesticide-free ecological urban gardening. The watering is performed with electric trucks. So the main problems we are facing with watering of the flower beds. So first of all, these flower beds have to be watered manually. This happens more or less twice per week during the summer season, and particularly when it's hot. This can happen even more than twice per week. So the watering is performed with small electric trucks, and is completely manual operation. It's indeed not possible to install some kind of fixed pipes, let's say, due to the way these boxes are made. And so there is a risk, or there is a problem, that is that we could use more water than actually needed, just to be on the safe side, because of course we don't want the flowers to suffer from lack of water. The city has tested some commercial solutions in the past, but these solutions were not fully satisfactory for several reasons. First of all, these were lock-in solutions, leaving very little freedom to the city. There is also a lack of added value in terms of knowledge, because this system, or at least the system that have been tested in the past, tend to work a little bit like a black box, and this system have a tendency to just tell the teams what they are supposed to do. And the system do this and somehow ignores the existing and important know-how of the professional gardeners that are involved in this work. And of course, one last problem that we encountered in the past is this lack of data interoperability, and also there are issues with the data accessibility and ownership. So the NAIADES solution for watering, in a nutshell, there are the several components that have been developed. Of course, there were sensors for determining the watering need of the plants. So these are humidity sensor and also tensiometer sensors. We wanted to avoid having too much sensors. So we know that technology is a double double-sided sword. It can become a sustainability problem by itself. So over-engineering, having too much sensors can be a problem. So we try to address this potential issue by limiting as much as possible the number of sensors. So we clustered the flower boxes, and we grouped the flower boxes that share the similar characteristic, like type of plants, type of soil, situation regarding the sun, and so on. So in order to have as few sensors as possible, and this sensor work with the LoRaWAN technology. Then we have a water flow sensor that is mounted on the water trucks. This allows to determine very precisely the amount of water that is being poured into the flower boxes, and it is equipped with the GPS sensor. So this water flow sensor system transmits this information in real time to the NAIADES platforms. We also have an environmental station, which is basically a weather station with some additional information, which is very relevant for plants. And we have, of course, the AI, so artificial intelligence system on the NAIADES platform that provides predictions of the required watering amount. So the goal is that we can achieve the optimum level of watering, and that we don't use too much water, and that we don't use too less water, let's say. So we want the plants to be well, but we don't want to do so by using too much water. So as you can see, these systems use data from different sources, and this is a very important aspect or feature of the NAIADES system. And yeah, we will discuss more on that later. And of course, last element is the human-machine interface. So an application basically with a user interface, which is basically a tool that the gardeners can use to gather the information provided by NAIADES, and it is a system that guides basically the gardeners when they are out for watering. So there are also a part of this application which is more focused on administrative tasks, and yeah, there are other features. I will try to go a little bit. Yeah, I will try to go to the next slide, but maybe one important aspect that I would like to stress here is that this application and the whole system actually integrates the gardener's feedback. So what we are trying is not to have a system that will tell the people what to do. We think that these professionals have an important know-how. So the system is rather trying to interact with this know-how and to make use of it to improve the water consumption in the end. So now we have a couple of screenshots of the application. As what we can see here, for instance, we have a map with some of the sensor located on the map. There are many features of the application which I will not go into detail now, like the help. The application is able to suggest an itinerary based on which plants actually needs watering. We can see that the system suggests the users which clusters need watering, and suggest is an important word here, because the whole system does not assume that the user will do what the system tells him to do. I mean, not necessarily. The system is made as an help, but it will also support the idea or support the case then when the user does something else, something that the system has not been suggesting. So this is another another screenshot of the watering application where the user can actually provide feedback. So tell, hey, the plants were too dry, or hey, I went here, I came here, but actually I don't think that the watering was needed. And then the system also suggests the quantity of water that has to be used for each situation. Okay, so that was the watering use case. Now let me switch to the second use case, which is the fountain use case. The Fontaine de Tours is an iconic fountain built in the 60s. It's located in the very center of the city of Carouge. It's very well known by its inhabitants and also very much appreciated by them. And during the summertime, it's more than a fountain. Actually, it's used as a wading pool and as a source of refreshment as such during the summer days, especially by families and children. Some facts about the fountain. We use tap water from the public network, basically. Because the fountain is also used as a wading pool, the water is treated or retreated like in a regular swimming pool. But of course, there are specific challenges due to where the fountain is located. So it's in a urban context, and of course, due to the fact that the fountain is outdoors. The fact that it's located on a urban context means that the risk of contamination is much higher. Also, the city staff is not present at the fountain all the time because it's not a swimming pool actually. So it's not easy to keep control over the quality of the water. So the city is responsible for the water quality in the fountain, and of course the water contamination can be an hazard for users, especially for children. And when the contamination is beyond a certain threshold, then there is the need to add fresh water. There is also, of course, the need to add more chemical, like chlorine and so on. And what sometimes happens, and what we would like to avoid, is when, in extreme cases, the fountain is too much contaminated and therefore has to be drained, and the whole water has to be replaced. So the capacity of the fountain is 150,000 liters. So it's a significant quantity of water. But in general, what we want to avoid is to have to use too much water, because basically we add water each time that contamination goes beyond a certain threshold. So the problems, as I mentioned already, are first the lack of continuous measurements, because the staff goes there just once or twice per day during the peak of the summer. Also, there was a problem of a limited set of parameters that were measured. So there was not a lot of chemical parameters that were measured before NAIADES. Also, there are some key parameters, such as chlorates or even bacteria, which are important parameters for the safety of the public, but there are no sensors actually on the market for those parameters. So another problem that we have is that there is a high fluctuation of the measured parameters. There are, let's say, a high variability of these parameters, and also the situation can escalate very quickly. And it's really important to be able to detect early any contamination issue. Because if we wait too much, then it's too late, and then even more water, even more fresh water has to be used. So the solution provided by NAIADES for this fountain use case, there are sensors as well here. There is an integrated sensor platform with a wider range of sensors compared to the previous situation, working and transmitting the information via LoRa every 10 minutes to the platform. There was also a novel development by Ibatec in Spain to try to determine the presence of chlorates using information from the existing sensors. So this is, let's say, an ongoing yet promising research. Another component, of course, here as well is the artificial intelligence, which will provide water quality forecasts based on the several criteria, and not only criteria coming from the sensor platform, as we will see. And beside the artificial intelligence, there is also a decision support system, which works based on the multidimensional criteria, and basically will help, is intended to help the operators by suggesting the decisions or the measures that should be taken based on the observed situation. And of course, there is also an HMI, so an application for the city staff and management, so that all this information can be presented to the staff. The goal, in a nutshell, for this use case are to improve the awareness of water quality. It's also, of course, to improve the sustainability by reducing the usage of fresh water and chemicals. It's to leverage the power of artificial intelligence and decision support system to overcome the problem of the variability of the measured data. So the idea is to be able to better identify a trend, a degenerative trend of contamination before the problem becomes too high. And on the other side, also to be able to differentiate between actual situation of contamination where the situation will likely degenerate, and situation which are just normal fluctuation. And of course, one of the goals of all this system in the end is also to reduce the required workload by the city staff. So this is very quickly screenshot from the application user interface. And yeah, I have to go a little bit faster, but this is the last slide. Okay, so before I give the floor to Eunah, I just wanted to make some general considerations regarding regarding what we have learned so far, let's say from our experience and from NAIADES. We know that smart cities are increasingly ubiquitous. This is a fact. So smart city actually means a lot of things. On a side note, smart city does not necessarily mean more technology or more sensor or more data, but as a matter of fact, smart city also needs or also implies that there are bigger and bigger amounts of data available or being produced in cities and sometimes by cities. We know that this data is more and more important because with data we can use a system like artificial intelligence, and of course we know that this opens the door to a vast set of new possibilities. What we observed is that, however, at least if we look at the specific fields covered by our two use cases, many, if not most, of the existing commercial solutions are what could be defined as a vertical solution. So a very specific solution to a very specific problem, for example, watering of plants. And more importantly, the data that this application consume and produce is kept in silos. It's very limited in nature, For instance, the application only used the sensor data, a very limited sensor set of data. And also this data is not shared and cannot be shared because it was never meant to be interoperable with other systems. We have seen, and I think we are proving that the holistic approach, which is one of the key ideas of the NAIADES projects, is highly beneficial to the use case of these pilots, and I'm sure also in the other pilots that we will see later. We know that we see that the NAIADES platform clearly brings an advantage over a solution that do not have this holistic approach. And we see in general that a solution is smarter when it takes into account as many sources as possible, including, as we have seen, the feedback and the know-how of the humans. So a holistic approach is basically what can make smart water manager, smart water management even smarter. So this holistic approach. If we try to look at this problem in a larger perspective, if we not only think in terms of one smart city, but we observe and we think about many smart cities, I think the natural question is how this holistic approach can be scaled up. How can we go beyond each individual smart city solution and really share this data even beyond each city, with knowing the advantages that this can bring? And I think, but I don't want to anticipate that one of the answers is, of course, interoperability. And so it is my pleasure to give the floor now to Eunah, who will talk more in detail about the interoperability features of NAIADES. Thank you.
Eunah, you have the floor.
Hello, can you hear me?
Yes.
Okay, great. Hello, I'm Eunah Kim from UDG Alliance. We are a technical partner of the city of Carouge. I'm head of the research and development of the organization, and also as a board member of IoT Lab, one of the representatives of Fire IHE-Delft, which is working for the local communities to go to the data innovation. And also I'm a science advisory board member of Fire, which is recently launched out. And also I'm an independent expert of the European Commission. I think that Maurizio already gave an excellent explanation what city of Carouge is challenging of, and then he also concluded the key as a data interoperability. So I will go very brief. This part that I'm trying to introduce what we are doing in NAIADES for the data interoperability. I think we already saw that the keyword from the Thanasis, our coordinator's presentation on this. Like many of the intelligent projects, we also have data from the city side, and there are also open data and from the sensors and IoT devices, and inside the cloud we build the intelligent enablers, and eventually we hope that it goes to the city side. But I think I do not see the screen is moving from your side, although I changed the slide. My slide doesn't move somehow in the screen side.
Can you please go into full mode?
I did in the full mode, and I did into the full mode, and seems like it doesn't reflect my slide to the screen. I do not see it. I don't know what's going on here. Wait a sec. Sorry for this problem. But I'm now moving, but it seems like I do not see the screen is moving. Yesterday we tested and it seems like it's perfectly moving, and now it doesn't.
If you wish, I can share my screen.
I think that's maybe the safe side to keep the.
Okay, no problem. Okay.
Oops, sorry, I now have to.
Can you see my screen?
Yes, now
Yes.
okay, then we can go to the next page already. Just yeah. Then this is what I explained, that we basically have a cities and then enablers and cloud. Yes. Then could you just click on? Yeah. Then the problem is that there's a many. Sorry.
No.
Can you? I can hear somebody talking.
Okay.
Is there any problem?
No,
Okay.
we can hear you. It's okay.
No.
There is some background. Someone is.
Yeah. Then
can
please
see.
go to the others, like a slide mode, please. Yes.
Επειδή μπορεί να υπάρχει κάποιο εσωτερικό.
If someone is talking, maybe we can mute that person.
Yeah. Anna, but can please go to the slide mode. Thank you. Then what we want to do is basically the data interoperability, so that all these enablers and then users, then how we could make the data interoperable, and then even not only this project itself, but when cities want to extend the project to the further, then how we could make each systems interoperable. I think that's the big questions we should make. And the NAIADES made it with the NGSA LD APIs and data models, so that we use the Orion LD context broker and Quantum Leap broker. Of course, this is not LD. They support LD new version, but I just put it there for emphasizing it. So previous one, that if you have NGSA V2, then this LD version supports all the V2 and LD API, so that you could make data interoperable. And there is a next slide, please. And of course, the most important thing is that you should make a data model also standardized, so that it's not only NAIADES itself's work, but it's we have 5 other projects in the smart water, and then we have one community to also invite the other experts, so that we build data models together regarding the water sector needs. And then there's also existing data models, so we use it, and then you see the NAIADES extension at the end, that you see that's the NAIADES extension, that we share these data models together with other communities. Next, please. Then why, among all the solutions, why we choose the NGSA LD? That's the ETSIS standard, and a lot of European cities actually use NGSA LD based of the data interoperable solutions. It's a very much of information centric, and what Maurizio mentioned before is when there is other project in different sectors, how you want to make it, the horizon interoperability, not the vertical one, so that this is from the user apps and IoT data or open data, and then it's all can be easily represent and with the JSON LD syntax, which is very easy to communicate with other systems. Next, please. And I brought from the European Commission the website about the context broker, so that the main things that when you use the NGSA LD API and the data models, data models is our ongoing work, and then with a lot of communities effort. But then this context broker itself is for the real-time data analysis, and then very easy to refer the context information to support with the diverse systems. Next, please. So that what we did was that we have now 3 cities, and the data management module is the core one to provide the data interoperability to support diverse intelligence services and applications. So whenever other city needs something, that the new AI modules easily just integrate in there as a modular component, and then the data management models will have this same support, so that it's quite easy to be scale and extend. Next, please. So then why we are emphasizing so much about the interoperability? This is the now few years old one, but I'm really I really like to bring this to the people to show that what kind of era we are living. There's different sectors, they start to have a different needs, and then they developed a lot of standards to make it interoperable. But eventually the different sectors have different standards, and then these solutions eventually need to be integrated and interoperable. And then how we would do that? That's the answer is what I showed that this with the context information management, and then just that's the only the data in a semantic way that we make interoperable with all these different standards. Each solution will develop with their own following standards, because they are all standards. But that's what we are doing. Next, please. So this is the ICT for water from the European Commission, the roadmap, and then NAIADES started in middle of the 2019, and then this is a version of 2018. They make a final version, and then can you click one? Can you click? Yes. Then that's the it's also very much focusing on the interoperability, and the data sharing is basically possible when the interoperability is implemented. Next click, please. So that there is some, with this goal, that a lot of emphasis on the data interoperable solutions, and then we have these common languages, and then also our solutions try to make a cross-domain data sharing mechanism. Next, please. So basically, that so what we could make with the data when we just focusing on the data interoperability, then with all different solutions, you can put any AI or other intelligence services or application, you can put it in. But basically with the data models, and then next click, please. We have this raw data from the Carouge, then we brought it, and then we changed the format to the modeling, and then we follow the API. Then now it's 2 applications Maurizio mentioned, in the urban agri watering and then public water quality from the fountains. We made it. And next click, please. Then next click. Yes. Then we have let's imagine of the new project Carouge want to make it, that they want, because they are really with this riverside, that with the climate change, this flooding has a new problem for the Carouge, as far as I know. And then imagine that if they have a new project, and then they could just add the new AI solution to analysis this flooding data, then they could easily just extend this current one, including the new use cases. And then the other side, let's say that the other organization, they want to work on the traffic assistance system of the city, then they follow the common APIs, then these kind of, next click please. And this kind of the imaginary project can be easily integrated with the common APIs and with the cloud system without much budget that city needed. It's not the new 2 projects, but they have existing projects, so they could save the money, of course, and then also the time-wise of the development, and then they could make a new project again with the integration. And then these things, the neighbor city, of course, can go and replicate the system with their own data, then they could make a similar use cases, or even the bigger area that you can make a reasonable sustainable development goal portal or some example. This is my just example naming. It's not the real one, but this kind of the data integration and federation is very easy with the data interoperability, and then you have a power of the ownership of the data, so that you can create the data innovation out of it. That's what we are want to doing in NAIADES. Next one, please. You can just click, click through. That's so basically now what NAIADES is doing is what Carouge, as you listen to the Carouge, that's the basically they check the commercial solutions, but they are not flexible and they are closed solutions. It's a vendor locking. So basically we want to do with the open standard APIs and common data models with the which one is not only for the project, but the whole community are working together, and with the interoperability managed by that, and then with the cloud and edge solutions, it's the scalable, is the guaranteed there, and then we provide some trust mechanism. And most important thing is that we listen the city's needs, and then Gartner's input is there. So it's a very much of customer-oriented solutions we provide. So on the development side of our platform is the naturally we follow the DevOps process. But then there we put this data as a key. So the data is always put there, and then with this DevOps cycle, always with the data, we make it the data ops as well. So that's the makes it easy to extend and replicate, and then exactly put the need of the customer, and then most importantly also it's quite fit to the EU's data policies. That's what I wanted to explain to you. Sorry for some delay with the technical problem on my side of the presentation. And now we go on to feedback session of the Carouge pilot.
Thank you. So I ask once again everyone to join the link that is on the screen over here, so that we can together answer to the next question. Eunah, if you could please just repost in the chat box the link so that everyone can join and press also from their computers. Thank you.
So that, yeah, link is in the chat box as well, so that you can click and then can go.
All right, and I will myself orient you to the slides. There we go.
Yes, so the first question is a quite general one. Actually, the two use cases in Carouge are interested in several ways. Of course, they are interesting from our point of view because they actually allow to save water, but because these two use cases are also well known by the population, it is somehow they can be somehow a way also to promote water awareness and a more sustainable water consumption. So this question is, which other activities, which activities in general could help, in your opinion, or based on your experience, which activity could help increasing the citizen awareness on water consumption? So it's a very general question, but maybe you have direct experience or novel ideas. And Anna, when you think that it's okay, I just let you
Yes,
move
thank you.
on.
So far we haven't received any replies, so kindly encouraging everyone to drop their ideas in the box. We're looking forward to everyone's feedback, NAIADES partners and external as well. Everyone is very welcome to join.
Maybe it can be not only about citizen awareness, also maybe workers or staff awareness, or in general.
Please remember to press the submit button once you are ready.
There are a lot of thumbs up in any case.
They are. Results are hidden, but so far the system tells us there are less results. Okay, well, let's see.
Yep.
Maurizio, would you like to provide some comments?
Yes, it's a lot of interesting ideas. Of course, I think many of the feedbacks focus on increasing the yeah, let's say the level of information by the public somehow. And then, yeah, it can of course also become political. That's clear. Schools are important fields. I think there is a lot of sensibility, hopefully. And of course, also water is something that maybe, at least in my personal experience, it's not. It does not receive. It doesn't cost a lot. So of course, this is also. I mean, one of the problems with something doesn't have a cost is that people tend to think that it will be there forever and it doesn't have any value. So. Yeah, but I think these are all very stimulating ideas. Thank you everyone for submitting them.
Shall we move to the next question?
Yes, please.
Oh, I just had a new reply as well. Thank you very much. We'll keep the results, of course, in the program, so we'll be able to go for them. So thank you very much. Okay, next question. This is a very straightforward question. Maurizio, if you would like to introduce it.
Yes, sorry. So simply, which one of the two Carouge use cases would be the most interesting for your city or your local situation? So A is urban watering and B is public fountain, or more in general, wading pool management.
All right. Shall we check the results?
Yes, please.
And we seem to have a clear winner.
Definitely. Of course, I think the public fountain is something quite specific, and also, yeah, it's a fountain, it's a wading pool, it's a swimming pool, it's an outside swimming pool, but with specific needs. But yeah, urban watering is probably much more. Yeah, it's a reality. It's much more present as a reality. So thank you very much, everyone, for your feedback on this. Yeah, so the following question is, why did you choose your previous answer? Yeah, maybe does it relate to some ongoing experience that you have in your local reality, or is it more an idea of something that could be done in the future? Do you also have maybe experience with existing solutions? Maybe, yeah, which are the aspects that would make this first or the second use case the more interesting for you? Which are the features of the aspects that could be more appealing, that are more appealing for you? And Anna, please feel free to move on when you want. I don't see how it's good.
Here are already some first answers. Okay.
Yeah, it's probably wider, yeah, applicable in a wider range of cities, of course. Yeah, that's of course there are cities. I mean, Carouge is a relatively small city. Then there are, of course, cases of much larger cities when also the distance traveled by the watering tracks is really big. So this optimization of the itinerary is something that I mean, it's also important for us, but it's even more important if we think of larger cities. That's, of course. And yeah, I think also that urban watering, it's something that will be very important in the future. I think that with global warming, there are like two contradictory needs. There is a need to make the city greener and to have more vegetables in the city, but at the same time, the constraints are getting harder to grow vegetables or flowers or whatever in the cities. So probably some help in better managing the water is definitely, in my opinion, something that has a future. Thank you. And so lastly, just please, there are several aspects, and we would be very we would appreciate to have your feedback on which aspects of those use cases are the more important for you. So we have a ratio of water saving, so the quantity of water that can be saved at the end. Help to increase the public awareness, the interoperability, of course, the optimization of the workload of the city staff, and improvement in water quality. So maybe we can think about improvement of water quality, not only for fountains or a wading pool, but maybe also more in general. And we will see who's the winner.
Ten more seconds, and I will show the
freezing.
All right, there we
And
go.
the winner is ratio of water saving. That makes sense, definitely. And the other criteria is quite yeah. There is user public awareness. Is yeah, of course. It's an important aspect because it can help. I mean, it brings awareness to citizens' home. Let's say so. And it can be applied on a larger scale, let's say. And yeah, also interoperability is quite important.
Okay.
Thank you very much.
Thank you very much for your participation in this first feedback or second feedback session. We can now move on to the next presentation from our speakers. And I will have the pleasure to give the floor to our speakers from Alicante. So Ignacio, I will make you the presenter.
Thank you.
And
okay, so yeah.
Please say a few words also about who you are.
Oh yeah. Well, I'm sorry, just 1 second. Okay. Well, my name is Ignacio Casals. I'm the Research and Development Manager of Aguas de Alicante. I have been working for more than 20 years in the water sector. And my expertise is mainly focused right now in water reuse, sustainability, circular economy in the water cycle, and also in the application of information and communication technologies to the water management. Okay, so Alicante is a Mediterranean coastal city, which is in the southeast of Spain. It has a population of more than 300,000 inhabitants, but it almost gets to double in the summer because of the tourism. Our company, Aguas de Alicante, manages all the urban water cycle, the drinking water production and the supply, the wastewater collection, and also its treatment at the wastewater treatment plants, and also the recycled water treatment and supply for urban irrigation mainly. The city of Alicante is subject to extreme weather events. We have long drought periods, and also from time to time torrential rains and fast floods episodes. Just to give you an idea, the average rainfall, the annual rainfall of Alicante is 300 millimeters per year, but we can get to have 200 millimeters in just 1 day. So it means that you can get to have 2/3 of the annual rainfall in 1 day. And so this is a semi-arid climate region, actually one of the driest in Spain. And it has no local water resources. For that reason, we have a commitment with the sustainability of resources, which is based upon the efficient distribution and use of water, and also in the water reuse, which is a key piece of our sustainability strategy. And finally, it's also worth to mention that we have sensitive coastal waters due to the importance of tourism and also due to the ecological value of the coastal area we are in. So this is our background. And now I would introduce briefly the use cases that have been tackling in NAIADES. We will see them in more detail later on. First of all, the first use case is the water demand forecast. What is the importance of this use case? Well, to begin with, the short-term water demand forecast, that is to say, the one which is giving us the predictions more or less for the next week, is used for operational purposes. That is to say, it allows us to plan the water production while keeping the optimized energy consumption. It enables us to plan also the water volume that must be stored in tanks for the optimal water quality and the demand supply. And finally, this water demand in the short term can also be applied to anomaly, mainly leaks detection, when we compare the water demand forecast with the real demand, with the real consumption. Whenever we see a difference there, it could mean that something strange is happening there. Then we also need the water demand for the long term. That is to say, by long term, we understand more than a month in advance. This is also used for operational planning, for instance, for the raw water purchase and for the and to plan the production of groundwater, and also for the company's financial planning, obviously. So very briefly, because it will be explained later on by Matej, the inputs for this water demand forecast are, on one side, the water consumption, in which we get the data from different district meters, actually from 7 district meters, which make up the pilot of NAIADES, and the weather data and the weather forecast. With this, we have the consumption, the demand forecast, both for long term and for short term, which enables us to do all this operational planning. And by comparing the short-term forecast with the real demand, we can also detect any anomaly in consumption. Okay. Sorry. Okay, yeah. So, well, yeah, just to give you an idea, this is the area. This makes most of the city center in which the pilot has been carried out. And on the right, you can see the connection between all these district meter areas, which are interconnected, and actually make a macro district, the 7 of them. Then we have the second use case, which is the detection of saline intrusions. And I would like to make it clear what is the importance of this. This is saline intrusion into the sewers, into the sewerage. And saline intrusion into sewerage can get to amount to the 12% of the water that gets to our 2 wastewater treatment plants for Alicante. Considering the energy costs of wastewater treatment, which are 0.5 kilowatts per cubic meter, and the energy costs of water recycling, just remember that I said that water recycling is a key element for water sustainability in Alicante, which are roughly 1 kilowatt per cubic meter. Then we get to the final figure that the estimated total economic cost of saline intrusion in Alicante sewerage amounts to 1 million euros per year. Furthermore, this salinity, this high conductivity in the wastewater limits the quantity and the quality of the recycled water we are able to produce. I would also like to mention that this problem is not just something that happens in Alicante. This is said by most coastal cities in Europe, and it's a barrier for water reuse. So with this in mind, we had the objective of detecting and monitoring the saline intrusion into the sewerage by means of flow and conductivity sensors and a smart data analysis based on anomaly detection. For this, we selected a pilot area, which is by the coast of the city. It has a high density of pipes, older pipes, and due to the water table level, it has a higher risk of saline intrusion. In this area, we have established 5 control points with different sensors, water level sensors, and conductivity sensors, which are located at the different inlets of these control points. And with this, we are able to perform an anomaly detection analysis in each point, and then by comparing the results for all the points in this area, we can do an expression analysis so that we are able to locate where these infiltrations are taking place and be able to solve them. Finally, we have the third use case, which is the municipal consumption dashboard use case. In this case, we are focusing our interest in the municipal, that is to say the public consumption, which accounts for more or less 10% of the urban water consumption in Spain. It's very similar. The case is more or less the same in Alicante, particularly. So we have noticed that there is a large potential for consumption reduction in this specific kind of consumption. I would like to say that for this reason, as we are aware of the importance of public consumption, right now, most consumption points in Alicante are equipped with smart water meters for remote reading of the consumption. But the problem is that due to the high number of consumption points, that is to say, actually in Alicante right now are more than 500 public consumption points, which make it very difficult to perform an effective control, and the factors which are actually involved in the interpretation of the data, that is to say, the different types of consumption points. We have schools, we have gardens, we have museums, sport facilities. So it's really complicated to compare all these different consumption points. And finally, we also found out that there is need for awareness campaigns based on real data. For this reason, we implemented a use case in which we will be using the hourly meter consumption per point based on the smart water meter readings, both for the present, that is to say, the last days, and also considering the historic record as a baseline. And we have mixed this with the context information for each consumption point. That is to say, which type of consumption point it is it a garden, a school, sport facility, and public offices, whatever. And the data needed to normalize the consumption, which is typically the number of users for that consumption point, or in the case of gardens, the size, the area of these gardens. With it, we have built a municipal consumption dashboard, which give us, and it will be explained in detail later on, which gives us the consumption evolution, the normalized consumption ranking per type. It provides all this information on a map view, and in brief, it gives us a comprehensive insight and understanding of the public consumption for the municipal managers. Additionally, we have created also a specific school awareness dashboard, which gives all this information adapted for the comprehension of the students, because we aim at boosting the students' awareness on their water consumption through their real consumption data, the consumption they are doing at their schools. And this will be tested in February on a water efficient consumption contest for the schools, which has been called the Water Watch, as you can see the leaflet to the right. And that way we will be able to analyze how this understanding of their own consumption impacts their efficiency of their consumption. And so I think that this is all, but you will see all these use cases in more detail now. First of all, with the help of Matej. So Matej, I will give you the floor.
Okay, thanks, Ignacio. Yeah, let me share the screen first. Okay, and then let's make this presentation mode. Okay, hello, my name is Matej Posinkovic. I'm a data scientist here at Jozef Stefan Institute from Ljubljana, Slovenia. And so Jozef Stefan Institute, JSI, is part of the NAIADES consortium and is responsible for developing various services, various AI-based services. Here for Alicante, I will be presenting two use cases. So-called UCA1, this is use case Alicante 1, which is the aim of this use case was to develop predictions for water consumption. So what we are trying to do is to predict the amount of water that will be consumed in the next day in the city of Alicante. I mean, in some of the districts, because the city is then divided into the districts, and we are making these predictions for various districts. And the other use case, UCA2, is focused on anomaly detection in various signals. So we have another use case, which I think will be presented by my colleague Babis. Babis, he's from the ICCS, but this is the following presentation. So let me first start with the UCA1 and the reason why. So a large portion of the water that is provided to the Alicante citizens is abstracted really far away from Alicante, 100 kilometers away or even more, and from very deep underground waters. So you can imagine this is really an energy consumption. It consumes a lot of energy. In order to optimize, so to reduce the costs, the Alicante city is pumping this water during the night when the electricity prices are low, and they are filling the water tanks in Alicante, and then during the day they are emptying these water tanks, and then again when the night comes they are refilling those water tanks, and so the process goes. So the problem here that the water has to be pumped very far away, and lots of energy is involved for bringing the water into the Alicante. And currently in Alicante, the predictions they are making, they're using the Excel program. So basically, it's they say, okay, today is Friday, the 28th, I think. And they go into the last year. They check the 28th. They look for Friday. There's some corrective parameters, and this method, of course, it's a good enough method, but such compared to the machine predictions, compared to the predictions that can be done by machine, of course, it's not as accurate as it can be done for the. So you can imagine, yeah, this predicting the quantity of consumed water for the next day is an important data for Alicante, because if they bring too much water, the water stays in tanks, it can get contaminated, and so they have to dispose it. And if they transport during the night too little water, then when they start running out of water during the day, they have to start pumping new water into their water tanks, meaning that they are using the daily electricity prices, which increases the cost of water transportation. Okay, so this is why they need the predictions. So how this is done? Basically, you have to have some time series. It means so this is past. So these are the values. They are denoting the past consumption within Alicante, and of course we have to have this historical data. We have combined this historical consumption with the weather data. For example, the below graph is a graph for temperature in Alicante, and yeah, we squeezed it in one piece of data, which is then pushed into the black box, which is kind of a synonym for the AI algorithm, which then produces the prediction for the next day. And so this is usually would be expressing the predictions with some kind of loss function, but maybe for a general audience, this is it's more intuitive to show on one graph the real data, which is the blue curve, and the predicted consumption, which is the yellow curve. And you can see that this algorithm works pretty well, which is also confirmed by the loss function, which is giving us pretty accurate results. So this is the UCA1 use case. The UCA2 use case is about finding the anomalies. Now, for example, the anomalies we could be looking for the anomalies in various data, not necessarily within the data as we are doing in Alicante, but I will be explaining here in Alicante what we are doing here. So we now already know that for Alicante, water is very precious. It's also kind of expensive to get into the city, which is why part of the water, which is, for example, if you go and take a shower, then the water that disappears in the sink, this is a wastewater that Alicante is capturing, is pre-processing, and then is reusing in some other cases, like, for example, irrigation, so watering the crops in agriculture, because if they wouldn't be doing that, so they would need to use fresh water, which is expensive, and so on. So for them, for Alicante, it's really important to be able to use this wastewater. Which are they doing? The problem they actually have is that if the salty water breaks in, it makes this wastewater unusable. So if the sea enters into this wastewater pipes, they can only throw away this water. And this is something they want to do it, which is why we are looking out for the anomalies in the wastewater. An anomaly, of course, is the salinity within the wastewater. Yeah, so just a small note, because I know that Ignacio is a little bit accurate on this. When I say system here on this chart, I mean everything. What water utility is working? It's the drinking water, is wastewater, is water for cleaning the streets, which is not the drinking water. It's water for agriculture, etc. So part of the water they want to use it for other purposes. Yeah. Within the system, so everything what concerns water utility. And so how we are doing this anomaly detection? So we first take the original signal. So what is the original signal? Once, for example, imagine you are going to take a shower, the water disappears in the sink. What happens then? So this water goes underground. And under the city of Alicante, at least this is how it's done in Alicante, there are several underground water tanks, which are being filled with this wastewater. And when these tanks are full, they get emptied, and they start refilling again. So they restart collecting the wastewater from all the consumers in the vicinity. For example, and the original signal could be very simple, measuring the level of water. So what is the level of water in this underground tank? This is one signal we are, for example, examining. The other signal we are using for this anomaly detection is measuring the conductivity, the conductivity of water. So probably you know that the salty water conductive, it conducts the electricity, while the non-salty water is barely conductive. So the more the water is conductive, the more the presence of saline water in the wastewater. So the conductivity parameter is one also very important parameter which we are examining, and could be also thought as an original signal here we are taking. So now we have this original signal, and we are converting this original signal in a variety of other signals. So these preprocessed signals, they are all derived from this original signal. They are just, somehow processed. For example, the original signal can be averaged. Or, for example, you could take only part of the signal on a particular hour of the day for all the days in the past. Or you could take, two signals, two water levels of two adjacent water tanks, and subcheck the signal. So this could be the third signal. And so from one original signal, you can really reproduce lots of preprocessed signals, which are then pushed, each of these preprocessed signals are then pushed into the anomaly detection black box, which is again a synonym for some AI algorithms which are performed there. And for example, imagine the above signal triggers an alert, and the two signals below, they don't. So you can get here at the anomaly detection level various combination of signals. So you could get one signal, 0 signals, 2 signals, 3 signals, etc. And what we are doing, we are simply we are simply counting the number of signals all these black boxes are producing, and creating and adding them at some point of time, and creating an anomaly, let's call it meta signal. So this graph is only somehow represents the logic, but for example, here you can think about these preprocessed signals, about you can have 20, 100 preprocessed signals, and then 100 anomaly detections. And but the basic idea is to transform this original signal into an anomaly meta signal, which is then examined, this anomaly meta signal examined and as a base signal whether there is anomaly or not. And if I give you an idea how this looks like, so as I was mentioning, the conductivity signal and water level signal, the blue line is the signal, and the red line is the anomaly. The anomaly is detected, so the anomaly meta signal. And you can see, for example, in this conductivity signal, in this red circle, that in the blue line, something strange has happened. So you see that there is something unusual happening here, and you can see how the meta signal is triggered and is significantly higher than the other signals are. So and the same happens. Sorry. Okay, and the same happens with water level signal. You can see that, for example, his water level, this is water level tank. You can see that it's being, so the level, this is, I think, centimeters, 400 meters on y-axis. And you can see that it's being filled and then it's emptied. It's being filled and emptied. And you can see at some point, this water level tank first is filled above the usual the usual level, and it's stretched and it's being filled for far more time than it usually does. And you can see how the anomaly signal, which in other cases is just a small signal, simply explodes in this use case and in this particular case here, and somehow detects the anomaly here. So okay, that was a really short overview of what we are doing in the Alicante use case. Thank you very much. And yeah, Babis, you are welcome to take from here now on.
Thank you, Matej. So Anna, can you please give me access to share my screen?
I would like to ask Aristoteles to do it because I have encountered some screen issues right now and I needed to restart my computer, so I don't have the access right now.
Okay, Babis, feel free to share your screen.
Thank you. Can you see the screen now?
Yes.
In full mode?
Yes, now it's in full mode.
Yes.
Okay, thank you, great. Okay, so the name is Babis Magoutas from ICCS, Institute of Communication and Computer Systems, associated with the Technical University of Athens, Greece. I'm a senior researcher there the last 16 years. And my expertise is in the domain of data-driven application development, behavioral change support systems, and recommender systems. So in the NAIADES projects, we are leading, let's say, the development of the overall framework for water consumption awareness and behavioral change support. Ignacio and Maurizio already presented some aspects of this framework. So overall, the framework includes different applications assisting different types of users to achieve, let's say, awareness, increase their awareness about water use and change potentially their behavior towards more efficient water usage. So the framework does so by leveraging data and AI services presented into the NAIADES, let's say, framework and platform, and also by using data structure in common data models, as Eunah described, allowing the interoperability and reusability of this kind of applications. So the applications are addressed to different stakeholders who have an application about cities, and city stakeholders wanting to make sense of water consumption data. Another one that are addressed to water consumers and in particular to students of primary and secondary schools. So these two applications are applied, let's say, and are relevant for the Alicante. And then there is another application addressed to city workers, as explained by Maurizio previously, who are responsible for the irrigation of public space. And this one is applicable to Carouge. So in this presentation, in the following slides, I will focus on the two use cases for Alicante. Okay, so regarding the first application, that's about, let's say, the consumption city dashboard, consumption awareness dashboard for the cities. Our approach is to provide this kind of awareness consumption tools and along with different mechanisms to allow the different stakeholders to better understand the available consumption data. So the main motivation here is that water utilities possess a lot of data, so big data, regarding water consumption in various public spaces in the city, but this kind of information remains underexplored. So, and while in parallel, there are different, let's say, public-private partnership projects where the utilities who have this kind of data available collaborate with cities and city councils to provide smart city platforms trying to exploit this information. So what we are doing in this project is to develop the holistic water awareness dashboard, supporting the officials, the public city officials, to better monitor and understand how the water is consumed in different areas of the city, and also in different types of consumption. Already As mentioned by Ignacio, different types include schools, sport facilities, gardens, and so on, and how also the consumption changes over the course of time. So different comparisons can be made among consumption points, different groups of consumers, different areas, and this allows the stakeholders to take informed decisions regarding water consumption mitigation measures, to monitor the impact of these measures as soon as they have been implemented, and get a better understanding of the situation in the city. So here you can see an overview of the dashboard. This is the main page. This is actually a map view that is actually the main page of the dashboard. It includes different consumption points. We are using different colors to indicate, let's say, how much its consumption point has changed in terms of water consumption compared to the previous period. So the colors range from light green to red. Also, the users can see the average daily water consumption for all the points in the graph view, and also some statistical information regarding the yearly consumption across the different types, and also how the consumption has changed for each one of these consumption points over the last year. The users can filter what they see in the map, so they can select only a particular type of consumption to be shown, while we have used the different types of consumption points to structure the menu, as you can see in the left, and based on the needs of Alicante, we have included there different pages for public gardens, municipal offices, and schools, and so on. So here is the view. At the bottom left, you can see the view of a particular consumption type. So here you can see, for example, the public garden page and the list of all the consumption points that are under this category. So a user can search about a particular consumption point to get more details based on the name of the point or based on the ID of the meter that is used in order to provide the metering information. So as soon as a particular consumption point is selected, let's say a detailed page that you can see at the bottom is presenting where the water consumption during the last week is compared to the one week before. The monthly water consumption during this year is compared to the one in last year, while also the users can see how the consumption changes in a daily, weekly, monthly, and yearly basis. Also, another functionality that is supported by the application is the generation of a PDF report, so that all the graphs and information are available in offline mode to the different stakeholders. Okay, so this dashboard has been developed in two different iterations in the context of NAIADES. We are now in the process of finalizing the dashboard. We got the positive feedback on the first version, since this was presented to the city stakeholders, and they have included the development of a TRL9 version of this dashboard into the Alicante's Smart City Plan. This is actually a plan that will be implemented in the context of a PPP project, where the utility of the city will collaborate with the city council to enable the development of the Smart City platform of Alicante. So the whole project includes a big investment of 25 million euros for the next 5-6 years. And as I said, this includes a TRL9 version of the prototype developed in NAIADES. So we're very happy about this, and because actually this will allow NAIADES to become a core element in the future development of the city, and also ensures the continuity of the project results. Okay, now moving to the next dashboard that is about water consumers. The approach here is to develop a web-based behavioral change support application, mainly targeting interventions at public schools, engaging the students, of course, with the support of their teachers in activities that aim to conserve water and increase their awareness, let's say, with respect to water use. So the main motivation here and the need that, let's say, drove the development of this application is that the utilities need to have access to ICT-supported consumption awareness programs to engage water consumers and in particular students in this kind of water conservation activities. So through the application that we developed, they can have access to behavioral change support campaigns, monitor the campaigns, and also assess their impact. The application includes different so-called behavioral change support strategies, which are actually strategies stemming from psychology that are used in order to change the attitudes of the individuals. And this includes self-monitoring, feedback, social comparison, meaning comparing the consumption or behavior of one school to that of another, the provision of rewards, and also suggestions in the form of textual messages. All of these strategies have been implemented within the dashboard. Actually, in the coming months, a competition will be launched in Alicante among different primary and secondary schools, where they will use this dashboard in order to get access to the result of the competition, and the best school will get some rewards at the end. So this dashboard includes some pages, leaderboard page, where the schools can see their current ranking compared to the rest of the schools in terms of both the absolute, let's say, consumption, and also the consumption change compared to the previous week. So they can track in an online manner the status of the competition and how well each school is going. Okay, so the dashboard also includes information about the consumption per hour and the total consumption per day of each school to provide some feedback to the students and teachers involved in the competition. While also, again, we have the functionality of getting all the information in a PDF report, let's say, document, where the teachers can print and use it offline into the interaction with the students. So in the course of a class, for example. A forum functionality is also including, so the teachers and the students can use this forum to post, let's say, some ideas about how to decrease the consumption in the school. They can also post information about the competition. And of course, all the posts are moderated by teachers who are responsible to accept, let's say, the post and allow them to be posted into the forum. So in terms of next step, again, we are now at the final phase of the project. So as I said, very shortly, the actual pilot will begin. The utility of Alicante is collaborating with local schools to launch the competition among both primary and secondary schools. So an important element that we'd like to mention is that we selected students as, let's say, the focus of this application for two main reasons. One reason is that based on the current state of the art and literature, there were several applications that were targeting the behavior of individuals and households. So we wanted to somehow fill this gap and experiment with students. And the second reason is that we think that by targeting users, we will have a bigger impact, since students will evolve actually to responsible citizens of tomorrow. So actually the attitudes and behaviors that they have potentially adopted during this pilot will follow them to the rest of their life. So meaning having an impact that will last over time, while at the same time they can transfer the knowledge and attitudes they shape in this pilot to their families, also leading to a cascading effect and the multiplication of the NAIADES impact. I think this concludes my presentation. So I guess now we can move to the feedback session. So I would like now to pass the floor to Ignacio to, let's say, lead this session. Ignacio.
Thank you, Babis. Okay, so please, once again, follow the link. Just remember that you also have it available on the it's also available on the chat. Okay. Okay, that's it. Okay. So first question is just about the context information, the context situation. I described it in the first presentation mainly. To which degree do the needs, the situation described for Alicante apply to your context? So from you have 5 different options. Well, one is just I don't know, and then you have from just not related at all to directly strongly related. So start answering. I think that we have 23 answers right now, isn't it? Maybe we can start taking a look at the results. Okay. Well, we're somewhere in the middle, at least now, but I see that there's 0% not related, so at least there's some degree of relationship. More or less half of the participants see some relation with the situation described for Alicante to the context, and then a bit less than half of the participants see close relation or directly related to the context, while 7% are not really sure about this. Okay, so yes, we move to the next one. Which one of the 3 use cases described, I mean the use case 1, water demand forecast, use case 2, salinity intrusion detectors, and use case 3, that's for municipal consumption, seemed more interesting for you, no matter the reason. Right now, we only want to know which one was more interesting according to your view. Well, I see even I see some sad faces, so I guess that some people feel that the problems the problems in Alicante are also shared by them. So maybe we can start taking a look at the results. Okay, so yes, it seems that the use case which is more linked to or more interesting for the attendance is the one for the municipal consumption dashboard, but the other 2 ones are equally distributed. We more or less, well, actually exactly the same figures for the water demand forecast and for the salinity intrusion detection in sewers. So, well, I think that at least the 3 of them got some attention. The next question is directly related to this one. Next, please. So, just remember which use case you selected as the most interesting one, and please tell us why this particular use case is of more interest for you. Maybe either it's directly applied to my context, or maybe it could be applied to a different use in my context after some modifications, or maybe I just like the innovation of the approach taken for the problem, or maybe the quality of the solutions. You can choose more than one option for this one. Oh no, sorry, I was wrong about it. It's just only one option. The preferred option then. Okay, next question. Sorry, can we see the results? Okay, so well, for most of you, the main reason to prefer the option you selected is that you like the innovation of the approach to the problem, which is nice to hear that this is something innovative. But I also see that for almost 27% of people, it could be directly applied to my context, which is also interesting to know. Okay, thank you so much for your feedback. Next question, please. And this is a question directly related to one of the use cases. How likely is that the water awareness dashboards, remember that we have the general one, the municipal consumption dashboard, and then we have the one which is most focused as the consumer and particularly at the schools, could be applied to our city. So from not likely to very likely, either, or maybe I don't know. This use case was selected as the one with most interest, so I recall. So, okay, can we see the results? Can we take a look at it as where they're going? Okay, well, at least most people said that it was at least moderately likely or very likely. And actually, if we add up the results for likely and very likely, they get most of it. So I think that it has a good score in terms of applicability. Thank you. I think there was one last question. Was it? Yeah, this is an open question. You have any suggestion to improve the water awareness dashboard that was presented by Babis? So open question. I'll give you some more time for this. Okay, maybe we can start see what the answers are. Well, I look at first. I like the first one. The ideas of how to go looks great. Okay, nice idea about the social media. I think that's a really great idea. Making it customizable, but the citizens themselves, that's always something interesting for dashboards. Further customized based on the profile of the intended audience, yes, that would be a plus. And yeah, I like that idea also. Nice. Some funny emoji or items, making it more funny for the nice achievement. Yes, definitely. At least for the younger children, it could be. And added advices for water compensation. Of course, that makes sense at all completely. Okay, letting consumer users compare the water consumption with others. Yes, well, actually, schools will be able to compare the consumption with other schools anonymously, but it will be available. Yeah. So thank you so much, because I think these are very good advices, all of them. And I think that we can move on to the next session.
Thank you, Alicante team, for your very interesting presentations and for the feedback session. So now we are going to move on with our final pilot from Braila. And let me grant the access to Iulian.
Iulian, you have the floor.
Thank you very much. My name is Iulian Mocanu. I work for the CUP Dunarea Braila Public Utilities Company. I work as a network administrator for the SCADA system and as a programmer as well. CUP Dunarea Braila is the sewage and potable water delivery and production service for the entire county. But this presentation focuses mainly on the city of Braila itself. The city is located on the, well, hold on a second, I have to move a few windows so the presentation looks proper. The city is located in eastern Romania. It is on the bank of the Danube, and the Danube is the main source of water for the city. It is an old city with a lot of history. Over the course of its existence, it's been many things. It's been a commercial hub, it's been an industrial hub, but in the past couple of decades, it has dwindled a bit from what it used to be. It is currently suffering a draining of population due to the opportunities that people have sort of drying up as time moves on. We hope to change that in the future somehow, but currently we are where we are. Over the past 2 decades, the Dunarea Braila Public Utilities Company has struggled to find ways to modernize and improve its methods of managing the city's water network. It has faced many challenges along the way, be they technological or bureaucratic in nature, or the simple fact that people are set in their ways and resistant to change. Only in the last couple of years has the company been able to begin implementing a modern water management system, one that seeks to limit water loss, improve overall quality in terms of both the water itself and the service for the end user. The principal pillar of water management for the city of Braila is the establishment of DMAs, or district metered areas, where all the water flowing in and out of an area is closely monitored. Currently, we have 13 such regions established. The process of creating them is actually quite slow, as it requires both the modifications of the water network and the installation of flow meters at each of the newly designed inlets to the region. All the data that is collected from these sensors is monitored in the SCADA system, which was developed in-house, and it receives data from over 150 locations within the city and the county, to the tune of around 25,000 parameters that are updated every 5 seconds. The system is also capable of processing data and generating reports of all kinds, the only limitation actually being the imagination of our programmers and the needs of the company. Through the system, we can quickly analyze data sent from every device within the water and sewer network for the entire county, not just the municipality itself. And we are now taking a more granular approach by integrating all the sensors that we are placing in each new DMA. We have been doing this for the past 4 years, and we are going to continue expanding this approach as time moves on. Among the newest of these DMAs is the one established in the Radu Negru neighborhood, which was created specifically as a test pilot for the NAIADES project. The region was chosen specifically because of its high apparent loss, the initial minimum nightly flow being over 145 cubic meters per hour, which was, it seemed to us as being a bit too much. The reason for such a high number, well, there are numerous reasons for such a high number. There are over 190 pipes in the DMA, comprising more than 27 kilometers of different materials and ages that range from freshly installed PVC pipes to 60-year-old cast iron lines. The region has seen many changes to its water infrastructure over the decades, expanding as needed by the current situation, not necessarily by a specific plan. And still, it is one of the most recently developed areas of the city, which with an average pipe age of around 40 years. To put things into perspective, there are DMAs with pipes that date back to the 19th century that are still in use. Every day, around 3,300 cubic meters of water gets pumped into the Radu Negru DMA from 4 inlets. As we experiment with simplifying and optimizing the network, we will sometimes reduce the number of inlets to only 3, and perhaps at some point in the future there will be a further subdivision of the DMA into just 2 inlets. This would allow us to better track water distribution and detect losses. However, we also have to balance this drive of optimization with the maintaining proper water quality, water age being a factor that we are concerned about. Since joining the NAIADES project, we've installed a host of sensors within the Radu Negru DMA, offering us insight into the behavior of the network and allowing us to more quickly detect anomalies from within our SCADA system. Previously, we were not able to properly detect hidden leaks until they had caused major structural damage to the area around them. Visual detection was the main method, which meant that we could only know about such leaks when we received notifications from the end user. So when water from a ruptured pipe would get to the surface, or when a road sank because of water erosion from a leak. We hope to leave those days as far behind us as possible, but it's still a long road ahead, and one with a heavy upfront cost. Apart from the infrastructure changes themselves, a large part of the cost comes from the second pillar of modern water management, the sensor telemetry infrastructure. Currently, we have 4 flow meters in the Radu Negru DMA of the Siemens MAG 8000 variety, 1 at each inlet. They monitor both the in and outflow as well as the pressure at the inlets. Although they have been quite useful, it's been a struggle to keep them maintained and functional. The inlets at the Radu Negru DMA were not specifically designed to house sensitive electronics. And regardless of their IP68 rating, these were not really designed to function in the way that they are. They have malfunctioned numerous times because of flooding. We are in the process of rebuilding the maintenance chambers that house the sensors to hopefully prevent damage caused by flooding in the future. Now, an alternative would have been to simply encase the sensors in waterproof materials, but well, that would have made on-site maintenance quite difficult, and maintenance in general quite difficult. The MAG 8000 series is also a bit prone to software failures, specifically the modem component, which can only be reset by physically taking the device apart. Thankfully, we've gotten really good at doing it on site, so we don't normally need to uninstall the sensor completely. And within the DMA, we have also 4 pumping stations that service the high-rise buildings in the area. These have their own pressure sensors, which have been providing data for several years. Sadly, only one of the stations has an actual water meter, so we only know how much water goes into one part of the buildings in the area. Through the NAIADES project, we've installed an additional 4 sensors for pressure sensors of the HWM multi-log variety. These are fixed sensors that are placed at 4 different regions in the DMA in the hope that they will be able to track pressure anomalies. Alongside them, we also purchased 4 HWM permanent noise sensors. These were placed initially in the same location as the new pressure sensors, but have since been moved around quite a lot as part of the calibration process for the NAIADES AI systems. The result from installing these new sensors have already been quite positive. By monitoring and processing the data, we were able to pinpoint previously unknown leaks, some having ruptured into sewer lines and draining away, meaning that we would have never seen them on the surface. This has allowed us to reduce the minimum nightly flow from 145 cubic meters per hour to just 91 cubic meters per hour within only a few months. This is a drop of 54 cubic meters per hour. As a single cubic meter costs us around €1 to deliver, mending that leak alone saved us almost €40,000 per month, greatly offsetting the cost of these sensors, leading to less energy waste and saving a lot of water, which is in itself becoming an increasingly more precious resource. Not only that, but the new telemetry data has helped us find new leaks with greater speed than before. On Christmas Eve, for example, A pipe feeding the high-rise buildings had ruptured. The pumps from the local station attempted to compensate by increasing speed in order to maintain the pressure on the building side. This caused a noticeable drop in pressure for all sensors in the area, as well as from neighboring DMAs. The change was easily noticeable through the SCADA system, as you can see the part encircled in red. And that allowed us to narrow down the area and fix the pipe. At its peak, the rupture had caused what we were expecting, according to historical data, to be a demand of less than 30 cubic meters per hour to increase to over 40 cubic meters per hour. That number would have likely increased had the leak not been detected and fixed in time. And when dealing with water that gets pumped out at over 4 bars of pressure, we can safely say that time is indeed money. So the sooner we are able to fix the problem, the better. Finding and fixing pre-existing leaks, however, is not something we are able to accomplish with such haste, since we lack complete data for the end user consumption, and a lot of our hydraulic models were calibrated with the existing flows and pressure data, which include leaks. We can't simply flip a switch and pinpoint leaks that have been around for months or perhaps even years, unless they dramatically increase in severity within a brief window of time, which is not a great situation either, but that's how we noticed them a lot quicker. To pinpoint these leaks, we've begun a thorough investigation using robot-driven cameras of the sewer network. You've seen a picture of them actually back here, that inspection robot that you see there. And this is our main method, because we have a lot of old asbestos cement sewer lines that have been ruptured due to breaches from neighboring potable water lines. The process of this inspection is quite slow and will take some time to achieve its goal. That's why we also employ noise sensors in order to find areas with higher than normal noise, in the hope that it will lead us to unknown leaks. This still does pose some difficulties, as there are noises within the system that we also need to account for, like our own pumps, for example, or transportation hubs nearby, industrial equipment, or other acoustic pollutants. Then there is also the problem of the sensor placement. Since a sensor needs to be placed on a pipe in order to record sound, there must be direct access to the network. There are many areas where such access is very limited, leading to suboptimal results. Thankfully, as part of the NAIADES project, we do have access to a component that is dedicated to building an AI system that is, well, it's capable of suggesting the optimal placement for such noise sensors, and even will help us better detect the source of the leak. And that will very likely improve the performance of this detection method. That is only one of the components of the project that we hope will improve our capacity to manage our network in the near future. The other ones are a system that will help us better predict the water demand, and one that will help us improve the accuracy of the treatment methods that we use to create fresh water out of raw water. We are only scratching the surface, though, both for the Radu Negru DMA and for the city at large. We plan on supplementing the number of sensors, both pressure sensors and noise sensors, in the near future, leading to improved accuracy and the coverage of a much wider area. The upfront cost, especially when scaling this up to the entire city, is still high and will often cause concern within the company. But the long-term goals are unmistakable. We do have results. Hopefully, we will be able to soon reduce the water loss in the Radu Negru DMA to the minimum possible value, and then use everything that we've learned from it and all the tools we've developed, all the procedures, to do the same for the entire city. The process is daunting, but it is necessary. I would dare say that it is vital to the well-being of our society. Thank you very much. I hope Clara is ready for her presentation as well. Let me stop sharing my screen.
Thank you, Iulian. Anna, can I have rights to present?
Yes, you just got them manually.
Thank you very much. How can I present my other? Okay, I will bring this here. Give me just 1 second, please. Yeah, I was sharing my other screen. Okay, can you see my screen now?
Yes, just please go into full mode.
I'm sorry. Just 1 second, please. I think I am sharing. Okay, can you see it now?
Yes.
Okay, perfect. Thank you very much. And I'm sorry, everyone, for this delay. So good afternoon, everyone. Thank you very much for attending this seminar. My name is Clara Maria Corso. I am a civil engineer from the National University in Colombia. I did a master's in construction management and water resources engineering. I started working in the water utility, the local water utility from my city. After that, to some entities about funding projects related to water. And nowadays, I'm making master's in hydroinformatics at IHE-Delft. So it's very nice. We're very pleased to share with all of you the work that we have been doing at IHE for NAIADES project. And what I'm going to show you in the next 15 minutes is some part of the research we've been working in with the support of Professors Leonardo Alfonso, Gerald Corso, Dimitri Solomatin, and with external support of Iulian Mocanu from the water utility in Braila. So I will support myself to start in the real loss reduction theory. So there are 4 activities that have been listed as key strategies to reduce water losses, which are asset management, speed and quality of repairs, pressure management, and active leakage control. So our research is based in a key concept from pressure management, which is the real relationship that exists between pressure and flow. In this case, we're talking about the leak flow rate. However, the strategy that fits the most in our research is active leakage control. So in order to define what is active leakage control, I will first talk about the opposite. The opposite is reactive control. And it's, for example, the cases when the water utility waits for a burst to see visible, for some citizen to call and to report, or to find it through the staff from the utility, but once it has reached the surface. And active control is the opposite, is making early activities, proactive activities to efficiently be able to locate the burst or the leaks that infiltrate in the ground and do not reach the surface. And it's precisely, this is exactly why they are so difficult to locate. So active control aims to reduce the runtime of hidden leaks, reduce the awareness time for new leaks, and this is done by 3 steps. The first one is awareness. Awareness refers to knowing that something is happening in the network. We don't know really where it's happening, but we know that there is a leak. The second one is detection, in brackets location, that refers to narrowing down the leaks to a certain area, identifying leak hotspots. And the third one is pinpointing, that is related to determining the exact location of the leak in order to dig and repair it in the lower possible time. Pinpointing usually involves specialized equipment and experienced staff, so this is not an cheap activity, usually is quite expensive. So to make it very effective and very efficient, first it's important to make a good detection or a good location campaign. So our research falls into this second step. And in this sense, our objective is to identify a group of nodes that define an area for pinpointing through a series of pressure measurements, as I'm going to explain later. Our case study is the city of Braila in Romania that was widely described at Iulian before. Some things to remark, three important characteristics of the Radionegro DMA showed here in yellow. It is a DMA with high water losses, above 40%, as it has been evaluated by the utility. It has multiple inlets. This DMA has multiple inlets, as you can see here with the yellow squares. There are also changes in operation. For making an example, when we started, it was like July, August. 3 of these inlets were working, Apollo, Radionegro 1, and Radionegro 2. GA Braila was out of service, and 4 or 5 months after that, there was a change between these 2 inlets. So it shows also how variable is the operation of this DMA. The other characteristic I wanted to remark is that the water that comes from Radionegro is pumped from pumping stations that are located outside of the boundary of the DMA, and that means that for the cases that there is water distribution between the pumping station and the DMA, the boundary conditions for Radionegro can become very variable, not only along the day, but also from one day to another. So it's something also important to have in mind. So going back to the instrumentation that we have here, then we have 4 pressure sensors shown here in red triangles. We have also 4 hydrophores shown in the blue circles. These hydrophores supply water to the residential complexes in the middle of the DMA in this area, and they have also pressure measurements upstream and downstream. So in total, within the DMA, we have 8 pressure sensors, and we also have data from flow and pressure sensors in the inlets. And all this data was used to make some adjustment in the hydraulic model that is the base for all the methodology. So the base concept for the methodology is, as we saw before, we have these 8 points, the 8 nodes in the hydraulic model that represent the nodes that have the real sensor pressure sensors in the network. We also have a hydraulic model that represents the actual condition, and that's why we call this model the healthy model, because this is the model representing how is everything working right now without further leaks. With this hydraulic model, we are able to know for any time what all the pressure values in all these 8 sensors. I mean, in all of the nodes, but specifically in these 8 sensors that we want to compare. However, when a leak appears in a given location of this water network, what happens is that the demand increases, the velocity within the pipes also increases, and there are higher friction losses that make the pressure to fall in all the points and, of course, in the sensors. This difference between the pressure when we are not evaluating further leaks, the healthy system, and the pressure measured when we have already simulated the leak is what we will be calling the pressure residual. That I told you before, I think that it's easier to see it in this graphical example. In this case, we have 4 examples in which we have simulated leaks in this network. The leaks you can see in the blue circles. This is the location of the leaks. The red circles represent the impact that these leaks have in the 8 pressure sensors. So this impact is measured as the difference on the pressure before the leak and the pressure after the leak. And as I told you, this is what we are calling the pressure residual. This is a term that I'm using a lot during the presentation, so it's important to have it in mind. And as you can see in these images, the combination of impacts from each location is different. So that combination of values, that combination of results is what we are calling the residuals vector. In this case, has eight results. With all these simulations and all these residual vectors, what we did then was to calculate the sensitivity matrix. The sensitivity matrix, it's something like I'm showing in this graph, where in the columns we have the sensor nodes, those nodes where we are taking the pressure values, and in the rows we have the leak nodes, that are the nodes when we are simulating the different leaks. So to make an example, each one of the cells or the intersections in this matrix are showing the pressure obtained, the pressure residual obtained in a sensor node due to a leak in a given leak node. In this case, it will be the pressure difference between the scenario before the leak and after the leak for sensor node number 1, when we simulate a leak in node number one, and in this case will be the pressure residual in node J for the same leak in node number 1. What I want to show with this is that every one of the rows from the sensitivity matrix is one of the residual vectors that we were talking about before. And for the case of Braila, we simulated 41 leak flows in all of the nodes in the hydraulic model, starting from 0.5 liters per second and adding the same amount every time. With the complete sensitivity matrix, then what we did was to make a comparison between all the residual vectors. For this purpose, we use some different approaches like machine learning and data analysis strategies. And the way that it works is the following. Let's say that we have two similar residual vectors. So we will expect that these vectors will correspond or will be representing two nodes that are hydraulically close connected. I am making an emphasis about hydraulically close connected, and I have an example to show my point here. This is part of the network of Rato Negro in Braila. As you can see, the yellow pipes in some points are not really, in some intersections, are not really connected to the blue pipes. What happens here is that one of the pipes is just going through over the other, but they are not really connected. So let's say that we have a node number 1 in this point, the yellow pipe, node number 2 in this point in the blue pipe, and a node number 3 in this point in the blue pipe. Even if nodes number 1 and number 2 are really close, especially, they are not so closely hydraulically connected as it will be for nodes number 2 and number 3, because the yellow pipe is not really connected to the blue pipe, as there is like a continuity between node number 2 and node number 3. So it is very important to think that not every time that we see water system, every intersection means a connection between pipes, as is the case of this DMA in Braila. And this is very important to take into account when we are analyzing the results of this methodology. So how does the leaking node prediction work? So let's say that we are aware that we have a leak in our system. We know that there is some burst, there is some leak, but we still don't know where it is, and that's what we want to find out. So we are taking a set of pressure values in the field, in all the sensors, in this case, in the 8 sensors that are available, and we are taking pressure measurements at times 0 to times 24. So one set of measurements every hour. From those values, from those pressure values, if we compare them with the healthy state that is being represented by the hydraulic model, we'll be able to get the residual vector that is characterizing that leak. Then the third step is to make a comparison between that residual vector and all of the training data that we got from the residual matrix. And for each one of those cases, we are calculating a similarity index. This similarity index is the one that is showing how similar are the vectors to each other. So the higher the similarity index, the more similar the vectors are, and this is leading us to where the leak is located. In this sense, the nodes that have the highest similarity index are shown like the most likely leaking nodes for that time t. Then the procedure is repeated for all the times, and in this way, the most likely leaking nodes are selected for all the times, and this will allow us to establish an area for pinpointing. In this example, in the right part of the slide, we were simulating one leak in this node, and the result of the algorithm is to say was to show these 5 nodes as the most probably locations of the leak. So this will be a good area for pinpointing for the next activity of the water utility. This comparison metrics is showing different examples. In this case, we asked the algorithm to show the 3 most likely leaking nodes. In this case, we asked for 5, and in this case, we asked for 7. The higher the number, the larger the area. But in any case, we can see how in some of these examples, the methodology was very accurate when predicting the leaking node. However, the last 2 columns are a very good example how a leak that was located in the same spot was accurately predicted or accurately located for a flow rate of 2.4 liters per second, but in any of the cases it was successfully located for a leak equal to 1.2 liters per second. These results led us to make a more detailed analysis. We got for the whole test data set general accuracy of 83%, but then we made some flow rate intervals. So we saw that for the lowest flow intervals, we got an accuracy about 10%, and it was increasing. It was increasing as the flow rate was also increasing. We found then 2 reasons for this behavior. The first one I will try to explain with this graph. Here we have in the x-axis the leak flow rate in liters per second, and in the y-axis we have the pressure residual. Each one of these curves correspond to one of the sensors that we are using for this exercise. And when we are talking about a high flow rate, we can see how the curves are spreading, and they are making a very representative residual vector that is easy to distinguish from other vectors, and then this is why the accuracy in these cases is high. But when we are talking about lower values for the flow rate, then all the curves are really close one to the other. And in these cases, it's very challenging, or it's more difficult for the methodology to be able to distinguish where is the real location of the leak, because a large number of the residual vectors will be very similar. In some cases, some will be, it will be more difficult to locate, and this is this reason is part of the explanation of this result. The other reason is that we all know that all instruments have a given precision and a given accuracy. So for low flows, for given low flows, some of them may not produce enough pressure friction friction losses, and therefore the fall in the pressure will not be gathered by the pressure sensors. So these 2 reasons are what explains the changes in the accuracy in our results. And finally, running out of time, something important to show is that for any water distribution network, there are some locations where a leak can be undetectable. It happens more often for low leak flows because of the reasons that I just explained, but still for some places, even when we are talking about higher flow rates, there are some locations that can be in any case undetectable. For the case of Rio Negro and Braila, we did these simulations, and we got that from the interval from 0.05 to 0.5 liters per second. 20 spots in the water network were not detectable. When we continue to the next interval from 0.5 to 1 liter per second, this number just fell down to 5 nodes. And from 1 liter per second and higher flow rates, it was maintained in four nodes. So the conclusion here is that it's not possible to talk about general threshold for leak location, talking about the flow rate. It will always depend on the characteristics of the water distribution network, how is the consumption, how is the operation of the network, also what is the location of the pressure sensors. So all of these parameters will have an impact in the definition of the threshold. Well, this is the advance that I wanted to show you so far. Further work for us will be to involve another techniques that can be also useful to apply with the residuals methodology that we have been working with. And with this, I came to the end of my presentation. So thank you very much for your attention. And I think that now we can continue then to the feedback session.
Thank you, Clara, for your presentation. Let's smoothly move right now to the feedback. I'd already shared with you the link in the chat box. And I will share my screen real fast for a final round of questions.
Okay, perfect. So the first, yeah, do you want to?
Carry on.
Okay. Do you consider that the use of artificial intelligence in leakage location and detection might be applied to your local context? This is a yes or no question.
Let's check the results.
Okay, great. That's great news. The second one, this is an open question. It says, what similar projects or experiences of artificial intelligence in leakage location and detection exist in your local context? Can be something very brief.
A lot of tears are being shed right now.
Yeah. Okay, no, so far I guess that explains the tears, but it's also an opportunity to start. Okay. Okay, the third one, what are the challenges to apply or to include artificial intelligence in leakage location and detection in your local context? What do you think that are the challenges? Okay, yeah, fair enough. That happens a lot in complete data. Putting all data in good order first. Yes, enough sensors, data and connectivity, good hydraulic models. Well, yeah, I think I agree with all of those.
And the last question would be from me. what would you say is the main cause of leakages in your city's water distribution? What is the cause, the reason why pipes tend to burst, or why certain components of the network tend to fail? What would you say is the leading cause? It appears the leading cause is pipe agent degradation, that's sort of the same for us as well. Thank you for your feedback.
Thank you, Braila team, for these very interesting presentations. Before we close the meeting, I would like to give the floor still to CERTH, our coordinator. Sorry about the tears. We will be back in a month, don't worry. For some closing remarks and a few closing questions.
Hi, are you hearing? Yeah, Anna.
Hi.
Are you hearing me? Are you seeing me? No.
Sorry?
Yeah. Can you see me?
Yes. If you could just wrap up real fast and ask the final questions we have for the NAIADES project.
Okay, have you shared the link for the final questions? Okay. So, which functionalities would you like to see implemented in NAIADES? We had presented the main functionalities of our project. So let's see what you would like to see. Decision support systems for leak detection. Yeah, sure, this is really important. Water domain, leakage detection, irrigation of flower beds. Yes, this is really helpful. Local reservoirs monitoring, online dashboards to explore results of the project. Yes, very nice feedback.
Thank you. Let's move on to the next question.
Considering what has been presented today, what is your perception of NAIADES in terms of maturity? There is a scale 1 to 5. Let's see the results. Okay. Very useful feedback. Considering what has been presented today. And also the maturity of the project. Very helpful feedback, yes.
Thank you very much, then, everyone, for your very relevant feedback. Elpiniki, I don't know if you would like to say some closing remarks?
Yes, Anna, I would like to thank you all the participants, for your really useful, helpful feedback that you provided to us and for your kind participation. Just a few words about what we learned so far from NAIADES project. NAIADES project defines a new ICT framework providing multidimensional intelligence on the water ecosystem through the introduction of artificial intelligence technologies. NAIADES focuses on data aggregation, unification, interoperability, as well as the distribution of data and intelligence. And on the top of that, it builds new data-driven technological solutions. The importance of these new technological approaches is manifold. The AI, artificial intelligence services, are not only replacing less efficient solutions, but are a demonstrator of the contemporary data-driven approaches. Next to that, the practical implementation of the data-driven services as a part of a natural cycle points out new challenges in the process of creating even more sophisticated data-driven solutions. Finally, the NAIADES marketplace is the key component responsible for demonstrating the range of existing services available at NAIADES to the public, including new end users and service providers. We really hope to have the chance to work with you in the near future, and thank you so much all for your participation and your kind feedback.
Thank you very much once again to everyone for attending. I know that some people have been connecting from even the other side of the Atlantic, which means a lot to us to get such a large representation. Once again, thank you to all the speakers for their time, for their very interesting presentations, and of course for everyone's participation in these feedback sessions, which were for the first time organized in NAIADES. So we hope to have more in the future. We'll be sharing, of course, the videos on social media, on YouTube, and we will have the slides on the NAIADES website. So thank you very much once again to everyone, and have a lovely weekend.